Okay. So now I'm recording it. Mm, you can see my screen, right? Can you see my screen?
Yes, sir.
Okay, perfect. So in the first of all, one thing that the deadline is for the submission of your first project report. Basically, title has been finalized, and now you have to submit the first project report, and that is due on 7th of October, right? Am I clear?
Yes, sir.
Okay. So now there will be regular submission of reports and your progress, and accordingly the grading will be done, because the overall weightage of the project is 30%. So all the elements will be carefully evaluated. Okay. Now, so in the last class we started discussing about the stretching and bending of beams. So we already started some discussions related to the boundary conditions and boundary condition on stresses and the displacement. And then we stopped somewhere when we said that this is a 2D problem. Basically, we are saying that sigma zz, sigma xz, and sigma yz, all of them are 0. So this is basically, you can say, plane stress situation. Okay. So if this is your x, y, and this is suppose the center line of the beam. Okay. What we are trying to evaluate is the axial deformation of the beam as well as bending of the beam. So basically, what we want to study is this thing, this green curve that you see here. This green curve we want to analyze. This is basically deformed shape of beam in the xy plane. So I have already done some initial discussions. Now, here are few assumptions, because this is a very complicated problem, and without putting some assumptions we cannot solve it exactly. So there are some assumptions. The first assumption is epsilon yy is 0. This implies that strains in the y direction are basically 0. But it does not mean that displacement in y direction is 0. Can someone tell why? Can someone give an example that strains in the y direction are 0, but the displacement in the y direction is not 0? So basically, if you see this beam, this displacement is happening along the y direction. So basically, uy is not equal to 0. But strains in this beam in y direction are 0. So when you are talking about this strain, okay, so you are talking basically about the cross section of the beam. So if you see the cross section of the beam, there are no strains in the y direction. So if you see the cross section of the beam, suppose this is y direction, so there are no strains. No strains means this section is not stretching or contracting in the y direction, but all the points on this cross section are uniformly moving in the y direction. That's why uy not equal to 0, but epsilon yy equal to 0. So this is first assumption that we make here. And second assumption is that epsilon xy is equal to 0. Basically, this is what? Shear strain in xy plane. Basically, this is also equal to 0. This is assumed that the beam, there is no shearing. There is no shearing happening in the beam. This is only purely deforming. Okay? So this assumption is something very important, and this assumption is nothing but the what you say is basic foundation of the which beam theory? I have told in the previous class.
Yes, sir. Euler-Bernoulli theory.
Very good. Euler-Bernoulli beam theory. So basically, this is assumed here. So with these two assumptions, now we first discuss about the displacement field. Okay. So for the displacement field, because all the displacements are happening in the xy plane only, so we are interested only in ux and uy. So first of all, uy, I have defined in the previous class uy. Can you please check your notes and tell me what was uy? Deflection in y direction, how you can write?
Sir, minus rho Vg.
Minus
Rho Vg.
Nu g, okay.
Upon E.
Okay.
Yz, sir.
Yz, sir. Very good. Excellent. So, so when you take the notes without thinking, then these kind of answers will be given. Can anyone correct this one? No? So basically this was something when we were discussing this problem. This problem. The deformation of a prismatic bar under its own weight. When we were discussing this problem, so you have told me the expression for this case. But currently what we are discussing is not this. We are discussing this thing, stretching and bending of beams. Did you find the mistake? Rahul?
Yes, sir.
Rahul, you gave this answer, right?
Yes, sir.
Yeah. So did you find the mistake? So now tell me what was uy when we were discussing this beam problem. Okay, no problem. So basically we defined it as Vx, some function V of x. It will depend only upon the x coordinate because this is the curve, deformed curve of beam. So this is x, this is y, and this is the deflected shape of the beam, which is given by function Vx. So uy is basically given by vx, which is only function of x. Now, the assumption that we made here was epsilon yy equal to 0. So is this assumption true for this case? It means epsilon yy is what? Del uy by del y. Now, this is del vx by del y. And this will be equal to 0 because vx is only function of x. There is no component of y. So del vx by del y will be equal to 0. So this assumption that we have taken here, because of that assumption only, we can assume that uy can be represented by this kind of function. Now, we want to write ux, which is slightly complicated. So please see this diagram very carefully. I'm going to describe here. If you see this diagram, so this is, let me switch on this one. First, let me, okay, I cannot erase, I don't know why. Keep, okay, let me erase this one first so that I can make more clear presentation. Okay, now okay. Okay, so here I show my laser pointer. So this point B is some general point on this cross section at a distance y from the neutral axis. Okay, from this axis. So we want to define the stress field on this cross section for any general point B. So at the time of deformation, so this kind of loading is being applied. Okay, this is a positive y direction. That's why loading has been shown in the vertically upward direction. Okay, and also the loading is being applied along the x-axis. So that loading has been shown here. If you see this one, this. So again in this diagram, okay. So when you want to write ux, you want to write the deformation ux of this point B. So when you will write ux, so because your beam, if you remember, I showed this diagram here, this diagram. So basically this beam is deforming in the x direction because of stretching, and also it is bending. Okay, so if you see any small cross section, any small element just like this, which is shown here, what is happening? This B, this centroidal axis is moving by this u. So this is basically u that you see here. So this center point is moving by u, and then this rotation of the beam is also happening because beam is deforming in the y direction. So that's why this rotation is also happening. Now this rotation can be measured as a slope of the deformed shape, which is minus dv by dx. So slope, we are using minus sign here because this deformation is happening like this. So because if you see the loading is in the vertical direction. So this deformation is happening like this, and that's why we are putting a minus sign for the slope. So if you see the net deformation, so basically from this point to this point, if you see here up till this point, the center to center is u, and then this portion that you see here, this portion is basically y into theta x. So that can be very easily calculated because this angle is theta x. So this will be y into theta x. And then if you put the value of theta x, this will be minus y dv by dx. So net displacement of B can be written as u minus y dv by dx. So basically, first B is going like this, and then because of rotation, it is again slightly coming back, which is y dB by dx. So that's how you define your ux. So ux can be written as basically u of x, which is the stretching of the beam, and then minus y dv by dx. V is also function of x, as we have seen here. So we can write the entire displacement field as ux x cap plus uy y cap. This is your displacement field of any point on the cross section. Now we can also write epsilon xx. So epsilon xx is what? Del ux by del x. Now, because you see this is only function of x. Oh no, there is a y is also there, but you want to differentiate it with respect to x. So what will be the differentiation? Shivans, del ux by del x, please differentiate and tell me how will you write the differentiation. Shivansh, are you here?
हेलो
Shivans, please tell me the
सर
differentiation of this.
सर
Yes.
मेरी में अभी तक शो ही नहीं हुआ आपका मेरा नेट लैग कर रहा है
Oh, you are seeing on mobile or laptop?
सर लैपटॉप पे कर रहा हूँ पर लैग कर रहा है आपकी आवाज
Okay.
कट कट के आ रही थी अब स्क्रीन पे शो हुआ है हाँ जी
Okay. Anyways, so now if you evaluate del ux by del x, it will be du by dx minus y d square v by dx square. Okay. So this is your epsilon xx. Now we can write sigma xx as E into epsilon xx, because strains are coming only in the x direction, and you can directly write just like a one-dimensional problem, E into epsilon xx, and this will be E into du by dx minus y into d square v dx square. So I have done nothing. I have simply multiplied E in the expression of epsilon xx. That's how you got sigma xx. So if you see this diagram here, in this diagram, is my screen lagging for everyone or only for Shivans? Is someone also facing the same problem? Shraddha,
It is fine.
is it okay? Okay. Saurabh,
Sir, it's fine, sir.
Shiva,
हाँ sir, it's fine sir now. Starting I also struggle. Like,
okay, okay. Rahul,
It's okay, sir. It's fine.
okay, and Vikram,
Yes, sir. Sir, it's lagging a
okay,
little bit for
okay.
me too.
So,
Sir, it is lagging a
pardon?
little bit for me too, Sir Shashank.
Okay, okay, it is lagging. Okay. So if it is lagging, please let me know. Okay.
Okay, sir.
So then I can slow down my speed. Okay, because that is a practical problem and I can't help with the lens.
Sir,
Pardon?
they can join after merit exit, sir. They can rejoin.
Okay, okay. So maybe you just rejoin as suggested by Saurav. Maybe that will help. Just try. I will wait for 2 minutes. I'll wait for 2 minutes. I understand this is a very difficult situation each one of you is facing. So those who are feeling some kind of lag, please rejoin. Shashank, is it okay now?
Yes, sir. For now, it is okay. Sir, but
Okay,
Shivansh
okay.
is saying that his
So I
meeting is
understand
not
that
being
all of
connected. No. Yes, sir. He is not able to
for
join the
Shivansh.
meeting also now.
Okay, then maybe he can join with someone in someone else's room if because maybe there is some issue with
Okay,
his
okay, so
then
then I'll
system.
ask him to join with me.
You ask him and he can come to your
Yes,
room and
yes,
he can
we are in
join.
the same room.
I Okay. So basically, I understand that with current situation of landslide and all those things, your morale may be little bit down and situation is not so good. But my only suggestion is that don't lose the hope. These kind of situations will keep happening, and this is something that is not in your control. Okay, and this is also that something will make you strong in your life. The situation will not be always favorable. There will be so many situations when you have to fight against the odds and situation will not be favorable. There may be depression because of these kind of situations, but my suggestion is keep working on your work, on your studies, on your notes, and that is something that will help you. Okay, you just don't feel that you are not able to come here, you are not able to study here, so it will have some effect on your studies. So as far as your emotional support is required, I can say these words to you. I understand it is really difficult and sometimes it may be very depressing that you are not able to come here, attend the classes. I understand totally. Okay. So, but that is the situation with everyone, not one of you. So, it is sometimes it may be difficult for even for the teachers to explain the concepts and to show the because describe the concepts and but what to do, that is the best that all of us can do. Okay, so don't worry, keep your spirits high, and these things will happen, and then one fine day these things will be sorted out also. So here I was discussing about the this thing, this sigma xx. So basically, if you see, if you cut a small section in this beam, so here you see this is sigma xx basically. This is sigma xy. This is qx. So basically, these stresses, if you take the resultant, they will provide you the shear forces, bending moments, and axial forces. So how can you write these stress resultants? Stress resultants. So you can write like nx will be basically integral sigma xx dA over area A. A is the area of the cross section. If you integrate this sigma xx over the entire area of the cross section, you will get nx. Similarly, bending moment, you can basically integrate y into sigma xx dA. So sigma xx dA will give you the force, and if you multiply by y, so this is basically moment of the force, of the differential force. If you integrate over the entire surface area, this will give you the bending moment at a distance x. Okay. Similarly, you can write shear forces Vx, and Vx will be sigma xy dA. So if you integrate this force basically, so you will get the shear forces. These are basically resultants, and A is your cross sectional area. That's how you can calculate your resultants. And if you see this diagram, this is the diagram that you have already seen during your BTech days, and there are very standard results are there, like dn by dx plus f of x is equal to 0, dv by dx plus qx equal to 0, and v minus dm by dx is equal to 0. So these three equations you have used significantly when you used to draw bending moment diagram, shear force diagram, axial force diagrams, okay, in your BTech days, in your structural analysis course. So I'm not going to derive them. So I'm assuming that you know that these equations are coming from the equilibrium of this element, and that can be proved. Okay, so this is, I think I'm taking for granted that you already know these equilibrium equations. Now, here comes something very interesting and that you have to listen very carefully. Basically, we know that epsilon xy equal to 0. This was the assumption of Euler-Bernoulli theory, beam theory, that shear strains are 0. If this is 0, then of course sigma xy will also be equal to 0, because this you can write like how? Mu times gamma xy, right? So basically this is directly proportional to epsilon xy, which is equal to 0. It means sigma xy is equal to 0. If sigma xy is equal to 0, what is Vx? Integral sigma xy, and this will be equal to 0. It means shear force is 0. So now here you see that this assumption is creating all these paradoxes. Now we also know that V equal to dm by dx, but Vx equal to 0. It means m is equal to constant. It means bending moment is constant throughout the beam. But this is not true. It is saying that your bending moment diagram is constant. So how it can be true for any general type of loading? It cannot be true. It means your beam theory is true only when your m is constant. So these are some limitations of the Euler-Bernoulli beam theory. Now, what we actually do? So we take V equal to dm by dx. Okay, so there was an equation, there were three equations, right? So there was this equation, dv by dx is what? Plus qx equal to 0, the shear force equation. This is coming from the equation of equilibrium in the y direction. This one, this equation. If you see this thing, if you put, okay, so dv by dx will be d square m by dx square. So if you put this one here, you get d square m by dx square plus qx equal to 0. So basically what we have done, we for v, calculating v, we are not using this. We are not using this. We are directly using this relation. So we are using this relation, and that's how we can write this one, and then we can write this one. So now basically we have two effective equations, equilibrium equations, that we need to understand. One is dn by dx plus fx equal to 0, which is governing the axial forces or stretching of beam. The second equation is d square m by dx square plus qx equal to 0, which is flexural stresses, which is governing the bending of beam. So we have these two equations. If we solve these two equations, we can get the stretching of the beam and bending of the beam. Now let us go ahead with these equations. So first we will start with nx. So we have written nx as sigma xx dA. Now sigma xx is what? We have also calculated sigma xx earlier. Can someone tell? Shivansh? See in your notes. Can you please tell in your note, from your notes, what we have written for sigma xx?
So E
E
du by dx
du by dx
minus y
minus y
d square v upon dx square.
Okay, good. So this we have written here. Now we will take E inside. E du by dx into dA minus E y d square v dx square into dA over A. Right? Basically I have expanded the integral. Now if you see this du by dx, and if you see this d square v by dx square, so these are only functions of x and they do not depend upon y and z. And your differential area dA is basically area of your cross section. So area of your cross section is what? dy into dz, and this is only dependent upon x. This is also only dependent upon x. E we have considered constant, or you can also say that E is only dependent upon x. This is also constant. So what we can write? We can write like this: E du by dx integral over area dA minus E d square v by dx square integral y dA integral over A. This is your basically expression for nx. Now I will write again here. So nx is basically EA du by dx, because your integral over dA will be A, area, minus E d square v by dx square integral over a by dA. So basically integral this thing y dA, this will give you what? Can someone tell what is this? Integral y dA. dA is some differential area and you are multiplying by y. So basically what you are trying to do, suppose this is your cross section. Yes. Moment of
area.
Moment of area. Very good. So which is also physically giving you what? Centroid of cross section. So basically if you also divide this with area, multiply by 1 by a, this will give you the centroid of the cross section, right? So centroid is basically this 0, 0. So what you have done, basically integral y dA will be equal to 0 for uniform cross section, symmetric system. This is basically equal to 0. If you put that, then you get nx equal to EA du by dx. So what was u? U was your stretching of beam as a function of x. So using this equation, you can relate the axial force with modulus of elasticity, area of cross section, and du by dx. Okay, so this is basically equation of stretching of the beam. Now similarly, moment can be written as y into sigma xx dA. Now again put sigma xx here, integral a y. So can someone tell what is the expression for sigma xx? Saugandh?
E
E
into du by dx
du by dx
minus y d square v divided by dx square.
y
d square v divided by
square by
dx square.
dx square. Correct? Is it correct or is it okay?
Yes, sir.
Okay. Y into E, this and then dA. Now let us expand this one. So how we expand? Ey du by dx dA minus integral a Ey square d square v dx square into dA. Now again E is constant throughout the cross section. Du by dx is dependent only upon the x, not on dA. So we write is E du by dx integral a y dA minus E can be taken out. D square v by dx square can also be taken out. Inside a we have y square dA. Now this will be equal to 0 because this is your centroid, and this gives you what?
Moment of inertia.
Moment of inertia. about which axis?
Centroidal axis.
About which axis?
Centroidal axis.
What is that centroidal axis? X, Y, or Z?
Y.
Is it Y?
Yes, sir.
Everyone?
Sir, x-axis.
X axis. Are you sure? Anyone else? So if you see the cross section, right? So X axis is something that is going inside the plane of this paper. And this is your Y axis, this is your Z axis, and X axis is going outside. So you are taking Y square dA. So a small section of area you are taking here. So this distance is Y, this area is dA. So basically you are calculating Y square dA. So this distance Y you are taking about Z axis. So your cross section is also rotating about Z axis. So basically this will be the moment of inertia about Z axis. Okay, so please don't make these small mistakes, otherwise there may be conceptual problems later on. So mx can be written as minus EIZ d square b by dx square. Okay, so IZ is moment of inertia about Z axis, which is your also axis of bending. Now we have basically sigma xx equal to E du by dx minus y d square v by dx square. So if you put inside, so you have written nx as Ea du by dx. It means du by dx is nothing but nx upon Ea. Similarly, you have written what? This one. So from here, you can write what? D square v by dx square as mx by minus Eiz. If you plug in these values here in this expression, you again get sigma xx as E. So du by dx is basically nx upon Ea, and then you have what? Minus y d square v is minus mx upon Eiz. If you put that, you get what? Nx upon A plus my. So E will also multiply my by Iz. This is your sigma xx. So this expression is quite familiar to you. So this is the expression my by I that you get for the flexural stresses in the beam. Nx upon A is coming due to the axial stresses in the beam, or basically this part represents the stretching and this part represents the flexure of the beam. So basically you have written sigma xx. Now ultimately we are interested in the deformations. So we want to write equations for deformation. Again, we go back to the equilibrium equations. So your first equilibrium equation was dn by dx plus fx equal to 0. Again, if you put the expression for dn by dx. So expression for dn by dx is basically your nx was ea du by dx. It gives dn by dx as e a d square u dx square. We are assuming that e and a do not depend upon x. So we are writing like that. Ultimately, if you put this thing here in this equation, what you get? You get e a d square u by dx square plus fx equal to 0. Or this can also be written as, if you do not want to put basically this thing out, e and a out, you can also write like minus d by dx of ea du by dx if e and a are also depending upon x, especially equal to fx. So this equation that you get here, this differential equation basically is equation of equilibrium in the term of displacement u. This represents the stretching part. Similarly, you can write d square m by dx square plus qx equal to 0. Now d square by dx square, the expression for m was ei d square v by dx square. Okay, there was a minus sign, so I have taken that out. So this will be like this. So this is, what is the order of this equation? This differential equation? Anyone? What is the order of this differential equation?
Second one.
Is it second order?
Fourth order.
Fourth order. This is fourth order ordinary differential equation or partial differential equation?
Ordinary.
Ordinary differential equation. Is it homogeneous differential equation or non-homogeneous differential equation?
Non-homogeneous.
Non-homogeneous.
No. Is it, what is the degree of this differential equation?
1.
1.
Degree 1. Very good. So first degree, fourth order, non-homogeneous, ordinary differential equation. Okay. So this should be very much clear to you. Okay. So that's how we get our equations of equilibrium in the terms of displacement. Now for given qx and given fx, you can solve this differential equation and you can get the expressions for u and v. So that is basically your Euler-Bernoulli beam theory, which you have already studied. Now we have derived in much more detail. Now moving on, I am going to talk about a simple principle, superposition principle, which is equivalent to eating a very big burger. So now, have you taken burger in some KFC and McD and Burger King and maybe some other brands I am forgetting. So you might have, of course, you might have taken big veggie burger or chicken burger, mutton burger, maybe something like that. Okay, hamburger. So then you might have seen where some burgers are very big. They are so big that they are even bigger than your mouth that you can take inside. Okay. So what you do? Sometimes you try to cut them, or sometimes what you can do, there is another way of eating that burger, that first you take the salad out of it one by one, then you take some one and few pieces of tomato or something like that, or chips if they are putting, you can take that separately, then the thickness will be slightly reduced and then you can open your mouth. So what you can do, so basically you can eat the piece, the big burger in pieces. So and ultimately you are getting the same amount of energy or your same amount of sensory pleasure even after if you eat burger in the pieces. Okay. So basically this is nothing but the superposition principle. You are solving one big complicated problem in small pieces. So that is the idea behind the superposition principle. So this superposition principle holds only for the linear elasticity problem. If you talk about the non-linear elasticity problems, this superposition principle does not hold true. Superposition principle is true only for linear elasticity problems. Okay, this is first rule. The principle of superposition can be used to represent a linear problem with complicated boundary conditions and or loads as a combination of linear problems that are equivalent to the original problem. So this is basically a complicated burger you want to break down into small pieces and then eat that. So that big complicated burger is something like that. So here you see, if this you see this thing carefully. So basically these are the loads. This is the load. This is one boundary condition. But here they have put one spring of stiffness K. And they want to solve this problem. To solve this problem, they can break in two pieces. The first piece is you remove the spring. You apply only simple UDL on a cantilever beam. So this problem is solvable. And the second problem is because this spring will try to apply, because this beam is being lifted in the upward direction. So this spring will try to bring it down. So this spring will apply a force in the downward direction at point A. So here they have removed the force, but they have applied the spring force. And then this is again a cantilever beam with a point load. And this is a cantilever beam with UDL. So with the combination of these two problems, you can solve this problem. So for the first problem, so let us try to solve for the, say, suppose we want to know the deflection at point A. That is, let us say, our objective. We want to know the deflection at point A. So for the cantilever beam, the standard solution that is known is Vx is equal to, Vx is deflection in the y direction, Q naught L4 by 24 EI 3 minus 4x by L plus x4 by L4. So this is basically a standard solution given in the literature for this kind of cantilever beam. For this kind of system also, standard solutions are available. So this is basically Fs L cube by 6EI 2 minus 3x by L plus x cube by L cube. So for those who are doing one, I remember that one of the group is doing project on making the app. Rohit Kumar Verma, who is doing this project? Those who are developing the app. Rohit.
Sir, second group.
Yes, sir.
Rohit, you are doing, right?
Yes, sir.
Okay. So Rohit, maybe when you develop that app, so this is the suggestion for you. So maybe in your app, you can show the working of the superposition principle also. So maybe in that app, you can put this thing that there is a beam or there is some problem, linear elastic problem. And then there are, you can break down it in two small problems and then you sum up. And that will demonstrate the superposition principle. If you can make that app, that will be also wonderful. So my suggestion is to your group that you please note down that thing, and I would like to see that superposition principle, application of superposition principle in your app. Okay. So now I will keep giving ideas to everyone, those who are doing this project. So all the ideas that I will discuss now, I will keep giving, and people can solve that. For example, another group, those who are doing pushover analysis, right? Vikram and Rahul.
Yes, sir.
Okay. So because you are solving a non-linear problem, but before that you have to also solve the linear problem, correct?
Yes, sir.
Hello. So my suggestion is that you try to find some complicated system, something like that. And for this kind of system, you develop a kind of a pushover curve for linear part. Okay. Just try using the superposition principle. So that is my suggestion for you. And who else is working? So I right now in my mind, but if you get any other better idea, you are welcome to do that. Okay. So now whole focus should be on making your project problem very interesting, and you have to apply maximum possible concepts that I have discussed in this course in solving your problem. So that will be really interesting, and you will learn much more. So now onwards, maybe I will not give any assignment. Okay. But there will be more and more emphasis on your project problem, because weekly there will be submission of your project report. Okay. So in that project report will be basically your assignment. So every week you have to work. So now this week you have to basically finalize your clear-cut objectives. Next week onwards, you have to develop the MATLAB codes or some basic calculations, and then there will be Viva. You have to come and you show your MATLAB code and how it is working, and accordingly the marking will be done. So that will be basically your assignment, and that will be basically your evaluation. Okay. So that is the idea. So now you have Vx for these two systems, and so let us focus at point A. So if you see point A, so x is equal to 0. So from the cantilever part, so basically deflection of A in this system and deflection of A in this system, if you sum the both, so you have to put x equal to 0 in cantilever part, in this part and in this part. So you will get this thing, Q naught L4 by ATI minus FSL cube by 3EI. Okay. Now the spring force on A is Fs, which can be written as K into VA. So deflection of A multiplied by the stiffness of spring. So if you put this expression, so VA becomes VA equal to Q naught L4 by ATI minus KVA L cube by 3EI. Now using this, you can write VA, the deflection at point A as Q0 L4 divided by Q0 L4 divided by 8EI 1 plus KL cube by 3EI. You can do that. Okay. So like that, you can calculate the deflection F. Point A using superposition principle. Okay. So I think now time is over, 8 o'clock. Okay. So all the best. Happy Dashera. Okay. And now we will meet on Thursday, right? So 8, 9. Am I correct? We are going to meet on Thursday, right?
Yes, sir.
Okay. Okay. So then Thursday means if I see, It is 6th of October. 6th and 7th. So midsem will be on 10th. Okay. So we have 2 days before the midsem. So I can cover more stuff. Good. Okay. So see you on Thursday. Bye-bye everyone. Saurabh, you want to discuss something?
Yes, sir.